Okay, thank you for introducing. So here, as compiler engineers, we are also working in the engineering work. And in the real world without computers, of course the real world contains computers, or is based on computers in the modern world. We use different materials for everything. So you see either wooden or glass or steel, and each material has its own purpose and its different purposes. But for software engineering, usually a lot of developers still think, which language am I going to choose and which compiler tool do I want to take? But with cross-language interoperability, we have the same advantage as in the without computer world, because we can also take different programming languages together and make use, so to say, cherry-pick the different possibilities of the languages. I'm Chris. I'm from the Johannes Kepler University in Linz in Austria. I'm standing here alone, but this is, again, a teamwork. So thanks to a fantastic team and also thanks to a fantastic supervisor, Roland Schatz. So the title is quite a bit long. The last part can be easily replaced by object-oriented languages. So it's about extending Sulong for object-oriented cross-language interoperability. And most of you now might think, what is Sulong? So we will start with this one. Sulong is embedded in GraalVM. Some of you might have heard it before, some not. So GraalVM is a big ecosystem, which is based on the Graal compiler. The Graal compiler takes Java bytecode and produces efficient machine code out of it, which means languages that can be compiled to Java bytecodes, such as Java, Scala, or Kotlin. You can directly use the Graal compiler with that. For other languages, there is the so-called truffle implementation framework. So if you want your language to be run in this system, you just have to implement this framework. So basically you implement an AST interpreter. And the Graal compiler is also designed such that this AST interpreter can then be compiled to efficient machine code. And the Sulong component here on the right-hand side is the LLVM implementation for this truffle framework. So with Sulong, you can execute LLVM bitcode. So you can think Sulong is kind of the LLI of GraalVM. Which means you have a lot of languages that can be run in one system, in one virtual machine. For LLVM currently it's C++, C, and Swift. And because every language is run in the same environment, they can easily call each other via cross-language interoperability. So you can call a C function from JavaScript, for example, or Python from Ruby, however you want. And the thing, how it works is the AST nodes are just put together, and if a certain part is executed often enough or interpreted often enough, it gets compiled down to a single machine code function, even if the source code is coming from different languages and is resulting from different files. And the truffle framework is built in a way such that this interoperability is almost given by default. So for Sulong, you have interoperability between LLVM and the other source languages. However, LLVM is not written by developers usually, but it's an intermediate representation. And what we would like to have is to have interoperability between the original source languages, C, C++, and Swift. And what is already existing is the approach for C, because C and LLVM is, of course, not the same, but the concepts are quite similar. And this has been introduced 3 years ago. So if you want to check out the talk, you can find it here. So what I did now is the extension for object-oriented languages, in this case for C++ and Swift. And the examples I show today live, so to say, in the area where the red arrows are. For example, I use JavaScript as the foreign language here. You could use Python, for example, also. And there were several changes necessary to make object-oriented source languages work. I cannot present everything today, so dynamic binding is just one of them. And we start with a Swift example. So we have a Swift class parent with a function square, which squares an integer, and then a class child, which inherits from this parent function. And of course, it's the same name. Just to show you where we are in the GraalVM big picture you've seen on the slide before. And of course, if we want to execute Swift code on GraalVM, of course, we have to compile it to LLVM first. So they get compiled. You also see the names get mangled, but nothing to care in this talk now. And if we want to use these Swift functions from another language, now JavaScript, we first need to get the reference to the Swift file. Then we create a Swift object in JavaScript, and then we just call the function. And the way how this cross-language interoperability works then is, this JavaScript code is executed or interpreted by the JavaScript run engine, GraalVM JavaScript. And if there is the call p square, then GraalVM JavaScript realizes by the Truffle framework that p is not a JavaScript object and forwards this automatically to the Truffle framework. And then the Sulong component gets the invoke message. But now, if we apply dynamic binding, because the methods in Swift are dynamically bound, of course, we do not know if we should invoke the parent or the child implementation of square. So this is the problem with dynamic binding. And the way how to solve this is, of course, I assume most of you know how a dynamic dispatch works. So instead of calling the function directly, we need to reference the v table. For Swift, it's also called the ISA pointer, but the virtual method table in general. And with the corresponding method index, we can then call the correct function. However, the thing is, we still don't know the method index, of course. And this is then really different on the source language. So for C++, the information is hidden in the debug information. So you have to compile the code with debug information. And for Swift, it is hidden in the global section in the method information, where the methods are stored as an element pointer instruction. So maybe enough slides, at least for now. So we're doing a live demo now. You can find everything at the GitHub link provided if you want to check it for yourself. So we have the Swift file on the left here with our child class and the parent class, and both have an implementation of square. So the parent square implementation is just squaring a number. The child implementation is squaring the incremented number. And then we also have a function to get 3.5, which is inherited as it is for the child class. And here at the bottom, there are just helper functions and helper classes to create Swift objects, because if we want to get Swift objects in JavaScript, we also have to need the methods for that. And then on the JavaScript file on the right-hand side, we create a reference to the Swift file. We also create the Swift objects. And then the code here is written such that the expected output is always written or printed first, and then we call the actual function. So we have some source files here, but first we have to compile the Swift file. And it's also important to include debug information. This now produces the file inherit with included LLVM bitcode. And now we can just run the JavaScript file and get the corresponding output. So there are some flags that have to be set that can be seen here. Yes, and you see the dynamic dispatch worked correctly. And what comes with GraalVM is also support for a profiler, for example, or now a debugger, which means with inspect, we can also inspect programs, and then we get a link which we can copy. Maybe I use the mouse here. And then if we paste it to Chrome, we now are in the JavaScript. I can set a breakpoint here, and then we can resume for the program to be in that breakpoint. And here see also the Swift file is already open. And the nice thing about the GraalVM concept is if we want to step through the program, we can even step across languages. Now we are in the parent square function, and we can return again. Also, an important aspect, the static type of the returned object is always the parent class. Therefore, also in JavaScript, you see also the type information is parent class, but still, if we step into it, the chosen function is the correct one. And this does also work in the other direction, but now I don't use Swift as an example, but I just use C++. So what we have here is a class accumulator, which serves as an interface with a field double with accumulated values and number of items that have been given to this object, and the accept method to provide objects, and get mean returns the mean. These are just dummy implementations here, so they are not needed because this is an interface. And we then have a process method which submits the numbers 1 to 4 to this accumulator, and then returns the number of elements, prints the number of elements, and then returns the mean. And for the concrete implementation, so the interface, so to say, is on C++ side. For the concrete implementation, we create 2 JavaScript objects, one for the arithmetic mean and one for the geometric mean. We again fetch the reference to the LLVM file, and then just call the 2 methods. And here again, we have to compile C++ first to the shared object file. And after compiling, we can execute the file. And also here, in C++, there is no, so we don't have to change the C++ code if we want to use it from another language. We can easily pass the JavaScript object, for example, and you see here that the results are calculated correctly. So that being said, I would like to restart the presentation again. Okay. Yeah, so you see with the object-oriented concept, we can simulate higher level languages, or the semantics of higher level languages. I showed now the dynamic binding concept, but there were also, of course, other things that I had to implement. But I have to say that the field access and to do the exception flow correctly in both directions, it was not that easy for Swift, and it does not already work for Swift. So this does not work yet. But in general, every time when there is a change in concept between the original source language from the developer's perspective to the language that GraalVM then gets, which is LLVM, modifications are necessary if we want to make this cross-language interoperability work. And everything I did is open source, so you can try it out yourself easily. So you see the links provided here. The slides will be published. So no need to copy it now. And I would like to thank you for your attendance, and now I'm open for questions. Thank you.
Well, thank you, Christoph. Do we have any questions out there? If not, then I do. So you can call from, you gave the example of Swift into JavaScript and vice versa. You can do this with C++ as well?
Yes.
C++ has some sometimes complicated promotion rules and conversion rules when changing from certain integer types to other integer types. Is there any way of dealing with that if you call a function that's overloaded in C++ with multiple types and it's quite mangled? Can that be resolved to the correct function from a different language?
So you mean for overloaded methods with different parameter types, or?
Yes, for example, if I overload something foo with both a character argument, an integer argument, a long argument, but you call it from, say, Swift with just a number, or JavaScript with just a number, is there something that will resolve which one to call?
Unfortunately, this only works if the number of parameters is correct. So if you just overload it with a different type, it's not really possible, because the thing is, I mean, for Swift is statically typed, so there it maybe would be possible. But if you get a JavaScript object in, JavaScript is dynamically typed or even untyped, and then it's not that easy to discover the type in advance. So then if you want to use this method, you have to ensure that there is only one overloaded method with parameter count. And of course, to go back for the example, for C++, the methods have to be declared as virtual. If you would not do this, so if the virtual was not here, then the except would actually call this implementation with the JavaScript object. So it would also work, but of course, this might not be the implementation you then wanted.
Okay, so it can call into things that are in the V table if it can identify the function in the V table. Very good. Any questions out there from the crowd?
Thank you for the talk. I would like to know, do you have any sort of performance penalty for dispatching all those calls? How fast is it compared to what you would do if you would run it in a single language, for instance?
Sorry, it's acoustically a bit hard to understand.
Do you have any performance penalty for doing these calls cross language? Or
any formal? Sorry.
Performance cost.
Performance. Yeah. Not yet already. On the one hand, Graal, the compiler, is dynamically optimizing, so the startup is really slow compared to the native version, which you might have seen. It will also be, and of course, there is a little bit of overhead in the whole system. If you're only using it for one language, the whole GraalVM concept may be slower, of course. This is something I will investigate in my PhD starting in 3 weeks. How to run code without this system when it's not needed, and then to switch to the system when it's needed. But I don't have concrete options yet. And it also differs a lot on the source language you use.
And we have another question here.
Thank you for the talk. I was wondering, you showed examples of pure functions, but what would happen if you pass a pointer to a function and the JavaScript tries to modify the memory value in the C++ code? Or, I mean, have you tried any of this?
This then also depends on the language. So every more complex object is automatically treated as a pointer in Sulong, so in the LLVM engine. But the thing how it works is, this has partially been explained 3 years ago. If you read a field in JavaScript from an object, then this is translated to a pointer offset access in C or C++, for example, and the other way around. So internally, there's a lookup happening, which field to need. Actually, I have to admit I have not tried if the pointers on C do not fit to the JavaScript objects on the other side. What happens? But yes, so for a complex JavaScript object, the C object or C struct actually has to be a pointer of a struct. and then it's resolved automatically.
Thank you.
Any further questions out there? And if not, then let's thank our speaker again.
Thank you.